Today in this video we will be discussing the remaining two colligative properties. One is the depression in freezing point and the last one is the osmotic pressure. So let us start with the depression in freezing point. What does it mean actually? It is very similar to the last colligative property, that is elevation in boiling point. In what sense? When we are talking about the freezing point, we know that at freezing point of a liquid, the vapor pressure of the solvent and the vapor pressure of the solid, they have to be in equilibrium with each other. That means if we are talking about a solution, at the freezing point, the vapor pressure of the solution will be equal to the vapor pressure of the solid. Here one thing I must mention, the vapor pressure of solid, if you are thinking about what it is, that means if you are talking about the solvent, remember, before mixing of a non-volatile solute, the solvent is in pure form. Nothing is mixed with it. When it is frozen, in that condition, the vapor pressure of the frozen pure solvent, that is to be considered, and that has to be equal to the vapor pressure of the solution if they are supposed to be in equilibrium. In a nutshell, if we want to define what is a freezing point, we should say the temperature at which the vapor pressure of the solid becomes equal to the vapor pressure of liquid. So here, vapor pressure of the frozen pure solvent will be equal to the vapor pressure of the solution. So we will see it graphically, then we will see it mathematically.
Let us see graphically. Here vapor pressure and temperature is being plotted by the two different axes. Now here you see with the with the black line, the frozen solvent is being plotted here, the vapor pressure of it. Then if you look into this yellow line, the liquid solvent's vapor pressure is being plotted, and with this blue line, the vapor pressure of the solution after mixing the non-volatile solute is being plotted. Now with the two arrows, I am just showing two very important points. The purple one is showing where the liquid solvent is intersecting with the frozen solvent. That means it is the freezing point of the pure solvent. And the green one suggesting that the frozen solvent is intersecting the line of the solution, that the vapor pressure of the solution. That means it is basically showing the freezing point of the solution after mixing with the solute. That means you can clearly see the difference between the 2 points, and in the graph further we will see these 2 points, TF and TF0. That is the difference between the two, where TF0 is having the higher temperature compared to TF. That means we can clearly say that freezing point of the pure solvent is obviously greater than that of the solution. So there has been a depression.
Here, if we consider that if the freezing point temperature of pure solvent, if we consider freezing point temperature of pure solvent, if that we are considering as TF naught, and at the same point of time if we are considering the freezing point temperature of solution, freezing point temperature of solution, that is TF only. So we have seen from the graph that it is the TF naught, this one. For pure solvent it will always be greater, and freezing point temperature of solution will be little bit lesser. So if that is delta TF, then we should be able to write TF0 minus TF, and this amount we can consider the depression in freezing point. It has been determined mathematically that the depression in freezing point, that is delta TF, is proportional to molar concentration of the solution. That means it is proportional to small m. Small m, remember, is the molar concentration of solution. So if we want to rewrite, we should be able to write delta Tf is equal to Kf into m. It is very similar to the elevation in boiling point. Kf, we should say it is the molar freezing point depression constant. So if we want to define it mathematically, the Kf, if we want to explain what it is, if we take m is equal to 1, then obviously delta Tf will be is equal to Kf. So we can say that the molar freezing point depression constant is the depression in freezing point for 1 molar solution. So we should say that this one, molar freezing point depression constant, it can be defined as the depression in freezing point. You can see it is the depression in freezing point for 1 molar solution. If we consider 1 molar solution, delta Tf will be is equal to Kf. So Kf we can define accordingly. Like the previous cases only, here also we can determine the molar mass of the solute from the depression in freezing point. So let us see how can we do that. So if we consider the weight of solute, remember solute we are considering as B. So weight of solute, if we consider as Wb gram, and molar mass of solute, if we are considering Mb, and weight of solvent, if we are considering that as Wa. So we know if we want to define the molality, it will be like molality is, means which is the small m, should be is equal to Wb by Mb, that is given mass by molar mass, into Wa over here, that means Wb by Mb into Wa into 1000. Do remember the definition of molality once again. You'll get to know that it is the number of moles of solute which is dissolved in 1000 gram of solvent. Now if we are considering this one in gram, it is to be multiplied with 1000. Means here if it is 1 kg, then that 1000 is not necessarily to be multiplied. Now we already know that delta Tf is equal to Kf into m. Now delta Tf, we are just writing this one over here. It should be Kf into Wb into 1000 divided by Mb into Wa. That means if we want to write Mb is equal to, we can write that Mb is equal to very easily Kf into Wb into 1000 divided by delta Tf into Wa. That means from here we can calculate the molar mass of the solute from the depression in freezing point data. So this formula will be handy in solving various type of numericals.
To understand the last colligative property, which is osmotic pressure, we need to understand what is osmosis. Osmosis is a phenomena of flow of solvent through a semi-permeable membrane from pure solvent to solution. Now what is a semi-permeable membrane? Now semi-permeable membrane means like animal bladder or parchment paper, is it can allow the flow of solvent and not the flow of solute. Here you can see with this that this is a semi-permeable membrane which is separating the pure solvent, which is water, and the concentrated solution on the right hand side. Now what will happen, as the semi-permeable membrane only allows the molecules of solvent to flow through it, so from left hand side the water molecules will come into the right hand side, as you can see on the left hand side of the photo. There is another term known as reverse osmosis, which you can see on the right hand side of the photo. It is the process of movement of solvent through a semi-permeable membrane from a solution to the pure solvent by applying excess pressure on solution side. Now in this similar condition, from left hand side the pure solvent is going to pass through the semi-permeable membrane through the solution side. So on the right hand side you can see an excess pressure is developed. This excess pressure is known as the osmotic pressure. So in order to define what an osmotic pressure is, we must say that the excess pressure which must be applied to a solution to prevent the passage of solvent into it through a semi-permeable membrane. Here you can see in this diagram on the right hand side, extreme right hand side, here you see the osmotic pressure is applied to stop the osmosis process. It's a very good example to understand the process once again. See to it. See here in the test tube we have taken a 4% of solution, and obviously from higher concentration to lower concentration the solvent will flow. So where the concentration of solvent is higher, obviously here in the distilled water, and inside the solution obviously the concentration is less. So you see we have taken a Thesel funnel, which is a selective semi-permeable membrane over here. So with time the water will flow through from higher concentration to lower concentration. This is the osmosis process. So in distilled water, again I'm telling you, the concentration is higher, and within the solution the concentration is lower. So you can see the driving osmotic force is towards the test tube, the upper layer of the solution. So magnitude of the concentration gradient will actually determine the case. What is a concentration gradient? We will try to understand that the concentration gradient means we cannot make the high to higher, but what we can do is to make the low into a lower one. That means where the concentration is low, we can decrease the concentration of water. That means from solvent we can pass the water into the solution. If we take a 10% solution, if we increase the concentration of the solution, more amount of water will flow into this semi-permeable membrane into the solution part. So I have chosen a better, simpler way to understand the process. Here you see it is divided, the two chambers are divided by a semi-permeable membrane. On the left hand side we have taken the distilled water, and on the right hand side we have taken the 4% salt solution where the water concentration is less. Now see what happens through this semi-permeable membrane. From left hand side it will only allow the water to pass through. So now see from the left hand side the water molecule will pass from higher concentration to the lower concentration of the water, of course. So from this side, from left hand side, you can see the water molecules can pass through into the 4% salt solution. Now see what happens with time as the water passes through SPM, because SPM only allows the water molecules to pass through, that is the solvent molecule, the amount of distilled water on the left hand side will become lesser, and obviously the amount of solution on the right hand side will become higher. Now the weight of the water column will increase, and that is the driving osmotic force that we were trying to understand. Mathematical expression of osmotic pressure has been given by scientist Van 't Hoff at 1887. So he has calculated that the osmotic pressure is proportional to C, which is the concentration, and also it is proportional to the temperature. So combining these, we should write that pi is equal to K into C into T. That K is the constant which is taken just to remove the proportionality term. Now we have seen that the value of K if we calculate that at different concentration and temperature, it is found out to be 0.082 liter atmosphere per degree per mole, which is almost equal to the value of R, which is the molar gas constant. So we should write that pi is equal to C into R into T, and this equation is actually the mathematical expression of the osmotic pressure. So here C can be also written as N by V. So if C is equal to N by V, that is the number of moles per volume, then pi will be equal to CRT as we already know. So pi we can write it is N by V into R into T. Now pi V is equal to N into R into T. So this formula will be another one which we can use for solving the numericals. Now if N is equal to given mass by molar mass, then the value of pi becomes is equal to WB into R into T divided by MB into V. So in this formula you see the molar mass of the solute is introduced. So from here we should be able to calculate the molar mass of the solute as we have done in the previous colligative properties.
Until now, we have discussed 4 types of colligative properties, and if you have noticed, in each case we have determined the molar mass of the solute. So through the colligative property values, we can also calculate the molar mass of the solutes. Numericals of those kinds we have to see. Now, the values of the molar mass will only be correct if the following conditions are satisfied. Number 1 is the solution must not be concentrated, because if the solution is concentrated, then what happens, the particles begins to interact with each other, and the values that we calculate will not be the same as we are expecting. And number 2 is there should not be, it's very important one, there should not be any kind of association or dissociation within the solution. Because what happens, if association or dissociation happens, the number of particles that we are expecting in the solution changes. Let us see how. See, in case of association, suppose there are n number of A molecules. In the solution, what will happen? They will give rise to A. Having n number of A will combine and will form this one. And this is only one molecule. Let us see a real life example. If we take acetic acid, say two molecules of acetic acid, they are having the ability to combine into this kind of thing. Two acetic acids will combine like this way. C double bond O, OH, CH3. So it's one acetic acid, another is over here. I have drawn it systematically so that it looks like this. Then obviously from this oxygen and this hydrogen, which is delta negative and delta positive, there is a possibility of forming hydrogen bonds here, and there is a possibility of forming hydrogen bonds here, and it forms a dimer. So here also and here also, due to the presence of hydrogen bond, they form only one molecule ring which is formed on this side, and this is stable. So that is how the acetic acid combines. There are a few other acids also which can do the same. So this is called the association, and due to which the molecular mass that we are expecting will not be the same. Now let us see dissociation. In case of dissociation, what happens? It mostly happens in case of electrolytes. Suppose I take electrolyte AB. So this is actually one particle, but if it can dissociate, it will form A plus and B minus. So from one particle we are getting two particles. If we take KCl, it will give rise to K plus and Cl minus. Similarly, if we take Na2SO4, it will give rise to 2Na plus plus SO4 2 minus. What does it mean? Depending on the electrolyte, the number of particles that will be generated will be different. So as we know, the colligative property depends on the number of particles. If the number of particles changes, as we have seen in case of dissociation, obviously the value will change. So that is why a new factor on 1886, Van 't Hoff has introduced a new factor called I, which is called the Van 't Hoff's factor. Let us see how this value, this I factor, will change all the formulas that we know in colligative properties. Let us see, after understanding the Van 't Hoff's factor, how does it affect to all the formulas that we know. Here I have written delta P by P naught, which is the relative lowering of vapor pressure, which is equal to the mole fraction of the solute. Next one is delta TB is equal to KB into M, which is the boiling point elevation. Then delta TF is equal to KF into M, which is the depression in freezing point. And the last is pi is equal to CRT, which is the osmotic pressure. Now, if there is any kind of dissociation or association, everything will be multiplied by a factor called I. So it will be I into XP, it will be I into this, it will be I into KF into M, and it will be I into C into R into T. Now, obviously, if there is no association or dissociation, I will be is equal to 1, which is the best case, ideal case. But for solutions undergoing association, so I will be less than 1, because more number of particles will be combining into 1. So it is for association, and I greater than 1 is for dissociation. So we have to keep both these factors in our mind. So all of you are requested to understand all these topics carefully. Questions obviously you can write on the comment section. You need to understand that depending on all these formulas, numericals has to be solved. Electrolytes can dissociate, some of the molecules which can associate also. In those cases, the I or the Van 't Hoff factor has to be considered, and the value of its, whether it is more than 1 or less than 1, more than 1 then how much, that has to be considered. So all those things will be discussed in the video related to the numericals.